Okay, so in the last video we've seen that CBC propagates bit errors into the plain text. So what can we do with that except for flipping information? Well, now imagine you have a ciphertext that you want to know the plain text of, and the ciphertext looks something like this: secret information, Rafflecopter, and then, as we've seen, the last block is always padded. So the recipient knows the padding, and knows what is padding and what is plain text. So now imagine we have an oracle where we can send ciphertexts, and it tells us if the padding of the plain text is correct or incorrect. This is a very plausible idea because in all crypto libraries that you can use, if you try to decrypt something and the padding of the plain text is incorrect, an exception is raised. Doesn't matter if it's in Python or Java or C++ or whatever, always an error is returned. And as you probably know, as application developers, we usually don't care about exceptions, and then the server might return a HTTP 500 or another form of information for us that the padding was incorrect. So now imagine we have the ciphertext, we don't know what's inside, but we can send it to a server, and the server either crashes if the padding is incorrect or it doesn't crash. So we flip the last bit here, we send it to the server decrypts it. Okay, this block is complete gibberish because we flipped a bit here, but the bit error is propagated to the next block, plaintext block. So now we flipped this padding from a 3 to a 2. What the server now does is he checks the padding, says, okay, last 2 bytes are padding, checks the other bytes, sees, oh wait, this is not a 2, this padding is invalid. Raises an exception. How can we use this as an attacker? Well, imagine now we XOR the last byte here with, not with 1, but with 2. We just try random things here. So what happens now is this bit flip, or this XOR, propagates to the last byte of the plain text. Well, now we don't get an exception because the last byte of the plain text, the padding, got flipped to a 1. Now the implementation checks, okay, is the padding correct? Last byte is a 1. Doesn't have to check the rest of the bytes because padding is only length 1, is correct. Therefore, we go back and return the value because the padding is correct. So we don't get an exception as a user. So what this means is we XORed the last byte of this unknown plain text with 2. Well, we now know that the last byte of the flipped plain text is 1. Why do we know that? Well, because the oracle told us that the padding is correct because it didn't throw an error. And because of that, we know that whatever the last byte was of the plain text, XORed with 2 is 1. We can just rewrite that and know that the last byte of the plain text was a 3, byte value 3. So we have recovered the last byte of the plain text just by querying this padding oracle, this binary oracle that tells us padding correct, padding incorrect. Well, next step is we do the exact same thing with the second last byte. We now know how we have to flip the last byte to get a 2 here. As this error propagates. So we just try out things now, and at some point when we have XOR'd things into the second last byte, we don't get an error anymore from the message because the second last byte is now a true as well. So now the padding is correct again. So we query the second last byte, try out all possible different values until the oracle tells us padding correct, and then we have recovered the second last byte, which is 3. So not so interesting because already from the last byte we knew 3, so padding has to be 3, so these last 3 bytes are 3. But we continue with this approach and go back to 4th until we flip everything to 4 here, the last 3 bytes, and now we try out different values here in the 4th last byte until the oracle tells us padding is correct. And if the padding is correct, this byte here was flipped to a 4 hexadecimal. Yeah, and then we have effectively, since we know, okay, this is now a 4, if we flip this, error propagates, this is now a 4. If we XOR this 4 with the value we had to XOR into the ciphertext to get to this 4, we know the plaintext at this position. The plaintext at this position is XOR what we had to input and XOR what it is now, and that is this calculation, that is 52, which happens to be the ASCII value for the letter R. So we have now, only with a binary oracle telling us padding incorrect, padding correct, decrypted the last byte of the actual plaintext, which is an R. And now we can do this attack, go on with this attack, and decrypt the entire plaintext, just with the binary oracle telling us padding correct, padding incorrect. So with this type of oracle, we can completely decrypt the ciphertext and also just fabricate new ciphertexts, even though we don't know the key, which is not good. So just by leaking padding correct, padding incorrect in the implementation, we have completely broken the security of the system. Well, how could an oracle look like? Well, it could look like this, for example. We submit a session with correct padding, gives us a 200. Submit a session with bit flipped with incorrect padding, gives a 500. Because if on server side an exception occurs, usually the web server returns a 500. 500 is the HTTP status code for internal server error. You can usually exploit this with Padbuster, which is a script to do exactly that. I have forked it to port it to Python 3. You can use it from my GitHub. Does this happen in reality? This is actually one of the most common vulnerabilities in cryptographic systems, CBC Padding Oracles. It happened, for example, in Apache's web server implementation of sessions. There was a mod called mod session that stored the session information on user side, encrypted it CBC mode, and you could use this CBC Padding Oracle they offered to just change your username to something you wanted to. Very common security vulnerability.